and welcome on today's video. My name is Wouter Pere and I'm the founder and main developer of GHEtool Cloud. And in this video I want to share with you our latest update on the heat pump module inside of GHEtool. Now, if you have been following us for a while, you know that in February of this year we added the option to simulate with modulating heat pumps inside of GHEtool. So instead of just simulating your bore field, you will now have the option that you can simulate your bore field together with your ground source heat. And the way we did that is we worked together with manufacturers to get more than 80 measurement points of each machine. And by doing so, we can create a highly detailed digital twin that was able to predict the efficiency of the heat pump at every part load condition and every combination of source and emission temperatures. And this gave you a very accurate way of designing bore fields, and also it calculated the seasonal coefficient of performance, the SCOP, for you. So historically in bore field design, typically this SCOP is an input. You define what the efficiency of your system will be, and that will be used internally to convert your building load to ground load. But now with this update, it was possible for you to actually let GHEtool calculate this efficiency for you. And if you change your bore field design, go deeper, add another borehole, and so forth, GHEtool can actually calculate the difference in SCP for each variation. So it was really powerful, and you, our community, really liked this feature. But we got one main feedback, and that it's all predefined. Because the models are highly detailed, you as an end user typically do not have all this measurement data available in order to define these heat pumps yourself. So that's why we work together with manufacturers. But the main feedback was that you wanted a way to do this also, to create your own heat pumps inside of GHEtool, which is actually what we will be talking about today. So today I want to talk to you about two different points. The first one is to define an emission temperature of your heat pump. So previously it was assumed that the emission to the building was 35 degrees, and for domestic hot water it was 55. Now with the latest update you can define this yourself. And this is really helpful to see, for example, the effect of going from a radiator temperature of 55 or 45 degrees to a lower emission temperature, for example for floor heating at 35 degrees, and see what the efficiency of your overall system will be when you lower this temperature. And secondly, what we will be talking about is a way to define your own heat pump. And we found a way that you do not need 80 measurement points for this, but only 3, which is typically given in the datasheet of some sort. Now, one note at this moment is that this methodology will only work for fixed speed heat pumps at the moment, because modeling the part load behavior, like we did in February with the manufacturers we collaborate with, that's not that easy and straightforward. However, we will be continuing researching this topic as well in order to find also a simplified methodology for that. And once we do, we will also implement it in the software. But before we can talk about point 1 and 2, we need to talk a little bit about the theory of a heat pump efficiency. There are a lot of things that influence the efficiency of a heat pump, but theoretically, the COP, the coefficient of performance, is called the Carnot efficiency, named to the inventor of this concept. And it's defined as the warm temperature of your heat pump, so the hot temperature your heat pump creates, divided by the difference between your warm and your cold side of your heat pump. And this difference is called the temperature lift. For example, if your heat pump is creating temperature at 40 degrees Celsius and it has a source temperature of 0, it needs to lift the temperature from 0 to 40. And this temperature lift is really important when it comes to the overall efficiency of heat pumps in general. Because the larger this lift, the lower your efficiency will be, because your compressor in your heat pump needs to work harder, so it will consume more electricity and your efficiency will be lower. And this is now implemented in GHEtool, that you can play around with this temperature lift. So you can also see the effect in overall efficiency when you're not heating your building at 45 degrees, but at 35 degrees. So that's already really powerful, and we will discuss that later in this video. But now for the simplified model, what we will do is we will take this theoretical efficiency, which of course is not your real efficiency, but at least it's correlated to your real efficiency. So a real heat pump will also have a lower efficiency when it has to go from 0 to 45 instead of 0 to 35, for example. And what we realized was that if we have at least 3 real measurement points from your machine you want to model, we can correlate this with the theoretical Carnot efficiency, and we can create a quadratic curve to correct the theoretical efficiency of your system down to the real expected efficiency. And that's what you will see here, or what you see here on the slide, and what you will see later on in the software as well. So here you see the red dots. These are the real efficiencies, the real COPs, as you can see on the axis on the left. And you have these yellow triangles, which are the theoretical efficiencies. And you can see that the theoretical efficiencies are way higher than the real efficiencies, of course. And then you have this blue line, and this is the correction factor to convert your theoretical efficiency that we know for all temperature combinations to the real efficiency. And you can see here that's between 50 and 60%. So our heat pump that we're modeling here has an efficiency that is between 50 and 60% of the theoretical efficiency. And when we go towards a higher lift, towards 50, 55, for example, in this case, our efficiency will be closer to the real efficiency, or our real efficiency will be closer to the theoretical one. And this is exactly how we are going to model your own, or you can model your own heat pump in GHEtool. You need to define at least 3 points. The more, the better, of course. But with these 3 points, it's possible for us to create this quadratic correction curve, and we can actually model your heat pump in all different combinations and use this correction curve to convert our theoretical efficiency back to what you can expect from your own machine. Now, with that being said, let us jump into GHEtool and show you how easy it is to define your own heat pump. So here we are inside GHEtool, and I created a new project for you. Now, without going too much in detail, we kept most of the default settings. We changed this to 0 degrees as a minimum temperature, and we changed the number of boreholes to a line of 4 boreholes. Now let's go to the thermal demand and talk about this heat pump module. And as you can see here, as we discussed in the past, when you want to work with heat pump data, being our own predefined modulating heat pumps are your own, you need hourly data. Now let us work with the default values for a second. Let's create an hourly load profile. We will do that in the city of Antwerp, for example, here in the main city center. Let's use this location, and then GHEtool can create an hourly load profile. Now, it does not really matter for us that in this video what the profile looks like. It's just we have an hourly load profile. Let's use it, and now we can use our heat pump database. And here we have the heat pumps of NRAD that were released in February, with more to come towards the end of the year. We have here now the option to enter the heating supply temperature. So that's also new, and that's what I talked about. If it's 45 or 35 degrees, we will come back to that later. But now you have the option to add your own heat pump. And the heat pump we are going to add is this one from the company Kenza. They make non-modulating heat pumps, and we are going to implement the one with a rated capacity of 15 kilowatts, because that's also the project we will be designing today. And this is a really nice data sheet because it defines the heat pump, the COP, as well as the available power at different condenser temperatures and evaporator temperatures. So let us jump back to GHEtool and click Add. Now this heat pump, I also have it here on the paper next to me. So if you're wondering if I memorized everything, I did not. So you can give your machine a name, and better to make this a name of the actual machine, because the heat pumps you define here will be available in other projects as well. So if you just call it the actual machine you're going to simulate, it's easier if you have another project and you say, okay, I want to use this heat pump as well. You only have to define it once. The other parameters you also need to define. So every heat pump has a minimum temperature lift. And for example, if a heat pump gets 10 degrees inside in its evaporator, it cannot create 10 degrees to the condenser. So there's always a minimum temperature lift, which we will set now to 25 degrees. There is also a minimum and a maximum condenser temperature, typically 35 and 60, something like that. And then we also have to define the delta T between the inlet and the outlet of the evaporator and the condenser. Now, the reason we need that is that internally in GHEtool we work with the average temperatures, as we discussed 2 months ago. But here, when you're talking about heat pump efficiencies, think for example about B0W35 at a typical ground source heat pump operation condition. What this means is it's 0 degrees coming into the heat pump and 35 degrees coming out of the condenser on the other side. But this means that on average, our evaporator would be a little bit colder because it goes in at 0 and it comes out, for example, -3, and the same on the condenser. And that's why you need to define here which delta T was used for the data so that we can correct this internally. Typically it's 3 degrees. And then here it states that we need at least 3 measuring points in order to create this heat pump model. So let us define a first one. It's at 0 degrees to 35. And then we have 15.5 kilowatts and 4.28. Let us go ahead. And again, I did not memorize it, but I can see it here. And you can immediately see the efficiency is plotted here. Let us go ahead and do the same with the point next to it, which is then 4.06 with a power of 15.4. And then our third point will be at 45 degrees at 3.4 and 15.4 as well. And now you see we have entered 3 points and we now already have this correction factor. However, if we add more data to it, and in the data sheet at hand there is quite a lot of data available, you will see that this curve gets better and better. Or that is to say, it is getting more and more accurate in predicting the efficiency over the entire working envelope of your machine. So this was actually the data for 55 degrees, it's 3.39 here, and it's 15.2 degrees there. And then perhaps just to make it complete, the final data point on the data sheet was 62 degrees. It was 3.08 as an efficiency, 15.18 as available power. So you can see here the quadratic curve correlating the real efficiency, the red dots, with the kernel efficiency. So let us go ahead and create this. And now inside of our database, we have here the commercial product. And here we have the heat pump we have defined ourselves. We can change it, but we can also now, just like before, say, okay, I'm going to use 1 machine of this, 2 machines of that, and so forth. For now, let's just use 1 of this, and let's work with 35 degrees as a supply temperature. Let's send it to the server, and it will start calculating the efficiency for us. Now, one thing to mention is we can also use these models for active cooling, but we only need to define them with heating. And that's because thermodynamically, when we know the efficiency during heating, we also know the efficiency during cooling because it can be converted. So you only need to care about the points given in the heating condition because we can refer from that theoretically also the cooling conditions. So here in the results, we have our hourly profile, and we see here that we have an average SCOP of 4.66 going down year after year because we have this slight imbalance as well of around -10 megawatt hours per year. Now let's call this scenario 1 35 degrees Celsius, because I said the other thing that plays a role in this latest update is that you can play around with the emission temperature as well. So if we now say, well, let's not work with 35 degrees, but let's say that the heat is supplied at 45 degrees. For example, there are still radiators of it, or it's a renovation context, and you do not have this floor heating. You can do it with 45 degrees. And here you will see that your efficiency is actually lower. We went from 4.66 to 4.15 because our heat pump has now a larger lift. The efficiency will be lower as well. So this, together with the option to define your own heat pumps, gives you a really, really powerful tool to go further again in the way you design your geothermal heat pumps. And as said, this is not the end. At the moment, this is only for fixed speed heat pumps, but we also want to implement a similar simplified model for part load data, so machines that do have modulation, that are frequency controlled. But it's not that straightforward. And a second thing that we also want to implement is that now these heating, but also the domestic hot water and the cooling temperatures, they are constant. But of course, your heat pump does not always give 45 degrees in this case to the building. And that will only be when it's colder outside. But when it's warmer, you perhaps only need 30 degrees or 25 degrees. And also that we want to take into consideration, because then we do not only have the influence of the ground temperature and the fluid circulating in the bore field, but also the fluid on the other side of the system. And that's also coming later this year. So stay tuned for that as well. I hope you found this interesting. Looking forward to hearing your feedback. And I'm also looking forward to seeing you in our next video. Take care.